Okay, so let's get started. So today we have two very special guests from Fanatics, Oleksiy and Bhanu. Right, they're gonna talk about how they build a cost-effective analytics stack at Fanatics with Apache Iceberg and StarRocks. A lot of comments here. Hello, guys. Okay, so Bhanu, I'll hand it off to you.
Awesome. Thanks everyone for joining. I'm Bhanu, a director of data engineering and data infrastructure at Fanatics. And I have with me Oleksiy, who's a staff engineer at Fanatics, and he's the guy who is kind of building StarRocks and Apache Iceberg at Fanatics. So I'm glad you guys are here. Let's talk about how we kind of transform the space of data and democratized it across Fanatics' complex ecosystem while making it super cost effective. So we have a very tight agenda. So we'll talk briefly about the data at Fanatics and how things were before, and then the challenges we faced, and what we considered, how the new architecture shaped up, and then how the results showed across themselves. A brief slide about me. I've been with Fanatics for over 7 years and have seen data in a bad shape to data in a very clean shape. So please do read about me in your free time. And Oleksiy is, as I said, is a staff engineer at Fanatics. He'll introduce more about himself. He's a master of many arts. So before we start, Fanatics is one-stop shop for all the sports fans to buy their licensed merchandise. We are licensed to sell sports merchandise across 10 different leagues, be it NFL, NBA, NHL, golf, soccer, WWE, all major leagues. Anything original that you're buying is predominantly coming from Fanatics. And currently we are close to about 100 million recognized customers who come and shop. We call it as the universe's largest sports customer database that we have. And we support 900 different websites and 14 million products SKUs for folks to come and shop with us. So we call them as Fanatics because we are very much for the sports fans. That's what we cater. And purely from a data lay of the land perspective, we support like there are 10 different domains, be it customers, products, experimentation, inventory, orders, you name it. There are 10 different domains, and across these domains there are 120K data sets. Not everything is a solid data product, but staging and production data sets we have about 120K plus. And 140 data products. These are the ones which power our data analytics and data decisions every single day. And we have a homegrown system called FanFlow, which captures all the business events that happens across the complex ecosystem. And there are 830 plus different event types. They're schema-full. And we get about like 1 billion events a day. Call it the click stream, and then even the backend systems, all the transactional events that flow into this, we capture about 1 billion of them a day. And the data scale is like in about a 6 petabyte scale. So it's a complex and a highly scaled system. That's where we are from a lay of the land perspective. And Fanatics has been there for so long, and back in 2000 about 2015 or so, there is this big initiative of being in the cloud, and we embraced AWS, and the data ecosystem basically grew organically, and things have happened in a very bespoke, siloed way, so that way we can support the business in a faster manner. But that created a mess in the data landscape. Fanatics is not unique here. Many companies fall in the same space. So we have data across fragmented warehouses. So we have Redshift and Snowflake as two warehouses that were used. and for different reasons. It started with Redshift, and then for data sharing, Snowflake became easier, and then we introduced Snowflake. And back in the day, there was no concept of Iceberg, so we were natively ingesting the data into Snowflake. So you have like two different warehouses. We embraced S3 as the data lake, which is a solid decision. And for data analytics, any of the queries the data analysts are running on Athena, the query latencies are extremely slow, led to frustration. We usually see a median query latency of 30 plus seconds. And because the data is spread across warehouses, joining these two different data sets across the warehouses is always a challenge. And because we are moving the data from Lake into Redshift into Snowflake, we are always creating redundant data copies, leading to write amplification, and which is not good from a cost standpoint. And importantly, like every other organization, real-time use cases are very important. At one point in time, we introduced Druid, so that way we can ingest the data faster and support real-time dashboards. But that came with the very serious limitations of you cannot do fact-to-fact joins, you cannot do primary key updates, and you cannot do point lookups, along with maintaining, while it can provide fast query latency, we also wanted to have these three as very important feature set that we wanted to have. And obviously maintaining Redshift and Snowflake, they were very expensive. The data warehouse costs were always going up. For simple use cases, we were burning like a lot of money. So all of this bespoke data transformation mechanisms, right amplification, and then no centralized ownership, it created a perfect recipe for data spaghetti and data silos at Fanatics. So mid 2022, we had a vision of basically simplifying this space in a very clean way. So that way it solves multiple things. Anybody is able to discover the data. They know exactly what data sets are trusted and what their SLAs are. And we give power to the data owners so that way they can maintain their data sets, but we provide a decentralized governance so that way anybody can come and figure out which data sets can be used for any further use cases. So we invested heavily on the data management and governance side. And then we wanted to provide safe paths for data access. So if you treat any organization into different personas, you'll be having data engineers, data scientists, business analysts, data analysts, and executives who all need access to data in different shapes. So how can we keep the space so simple that we have a paved path for every single use case or a bucketed use case? That was the important vision that we had. And we wanted to keep the platform and the infrastructure self-serve, so that way we can provide faster dashboarding and faster queries. And also now that AI is booming up so much, we provide natural language way of interacting and accessing the data, and then provide incremental data processing behind the scenes. So that way your cost of data processing is kind of super low. So that was the vision. We wanted to make the platform do the heavy lifting, and application and business teams really focus on their business use cases. So that way there is a faster mean time to market, and then we can improve the business quite significantly. That was the vision. And from the data spaghetti world, we simplified into largely this space. Oleksiy will talk more about deep dive into each of this. We embraced Apache Iceberg right from very early 2023, late 2022. And we wanted to consolidate Iceberg as our data format, table format. This actually solved the write amplification phase, because now many query engines, they support external tables as Iceberg, so that way we don't have to move the data. And Iceberg, as you all might know, comes with a lot of advantages of better partitioning, faster queries, inbuilt compaction features, so that way your health of your table on the lake is in a very good way, and it has very wide adoption. And we use StarRocks as our unified query layer. And this actually supports all of our real-time dashboarding needs, data analytic needs, even executives come and search on StarRocks. So StarRocks basically helped us in keeping the query latencies ultra fast, along with embracing Iceberg as our data lake. So that way we can get the power of Iceberg to the hand of users in a very, very easy way. And because of the real-time use cases, Kafka is obviously one of the key sources of data, the real-time data, and we ingest that natively into StarRocks for blazing fast queries. We used Glue as our catalog, so that way we have it becomes a centralized catalog for all data sets, and StarRocks would natively integrate that. And the data is kind of democratized because you can surface the Glue data sets on StarRocks pretty easily. For any incremental processing, we embraced dbt on Iceberg, dbt core. So very easy means for data engineers to define their problem statement as SQL. And then behind the scenes, the platform does the heavy lifting of incremental data processing. Superset gives life to the data because you can do dashboarding. And all the natural language queries, we are building agents on Amazon Bedrock. So that's largely the ecosystem. And as you can see, StarRocks really simplified our ecosystem, along with keeping the costs ultra low. That was a solution. I'll hand over this to Oleksiy now to talk about more internal details.
Hello, folks. Okay. So as Bhanu mentioned, we decided to use Iceberg as a foundation for our data platform. Any strong platform needs an even stronger foundation, and that's when we found Iceberg. At this point, open source technology, possibly not that old as some of others, but definitely on the rise, and with obviously a clear benefit. So what we were looking in Iceberg, so above mentioned data multiplication, but along with that, we looked at a durable store for historical data, a source for possible backups, restores, backfills, and again, the above mentioned data multiplication. So Iceberg going to serve as single source of truth. So we're going to resort to that in case we have we need ways to resolve conflicts or so. What we started with was creating Kafka to Iceberg sync. The previous diagram showed that most of our real-time and near real-time data is flowing through Kafka. And a good first step was to have most, if not all of this data captured into Iceberg. For that, based on our use cases, we used batching, and we created a Spark application that used external configuration for data transformations based on the source and destination, configured like in a flat file format, and then Spark was pulling events from Kafka in batches and was either appending or abserting them into Iceberg table. Important notion that we, from very beginning, since we had cases with the multiple updates where the data is constantly updated, and we immediately felt this penalty of delete files and similar Apache Iceberg specifics. So what we had to do is that we built the table maintenance into our application. So whenever the batch is getting inserted based on certain configurations and options, we are performing table maintenance right away, just to be sure that the data that we have is queryable. It has certain kind of smart logic, if I may say so. So for the hot partitions, we're not performing all the actions right away. We're waiting until certain partitions, let's say current day, is not hot anymore. So on the next day, we are performing most of the servicing on the previous day or days of partitioning. So it's been historically working well for us and very much economically viable. Moving on, so Bhanu brought a very high level vision of the best kind of practice in the field, which is the Medallion architecture of a lake house. I purposely made an image almost unreadable here because I would like to kind of take a very high level view of what it is here. So our goal was to have data sets split into those kind of pillars, right? The bronze, silver, and gold. They are of a different origin and they are serving a different purpose. But the main thing is everything is effectively later on goes through the StarRocks, whether this is historical data that StarRocks takes from Iceberg, whether this is something generated by DBT, or this is like a native store on StarRocks where we have real-time and near real-time data sets that might be used for like looking at the user behavior or so. So we took this as an example of where we would like to go, where we would like to land, and started building upon it. So a very important question, why CelerData? Why StarRocks? So you see kind of some names on the screen. We considered having something as an engine since Athena was not kind of serving our purposes so well, even though it is a good tool, but it could be costly and it could not be tailored to your needs the much as you can. And basically, OLAP databases like ClickHouse, they're not effectively engines, and they were lacking certain certain features that we envisioned at that time. And in here, I'm going to go a little bit back with what Bhanu mentioned. So we lacked joins. We lacked all the data being in one place to be able to join, slice, and dice it, and do things like you have a recent data in the native table in OLAP database, and this could be joined with historical data that is stored in Iceberg, for instance, right? So this is like a brand new capability that we wanted to have at our disposal as well. AMV and query rewrites stand as a feature that could be used for, I don't know how to put it, everlasting query performance or query speed improvements that could be done. So this kind of stand out for us. We did some POCs and we thought that this is a good tool that we can use to make our data sets meet the requirements of analytics or BI systems that we're going to be feeding. Integration with Glue Catalog was very important for us, and it is, as again Bhanu mentioned before, we have this pretty big Iceberg presence, and it is cataloged through Glue. And two-in-one, OLAP and engine. So at some point, it was like a no-brainer for us what to pick. So this is about our decision. So the next step for us was to establish data ingestion. Since we already had an Iceberg presence and we can integrate or access the data in Iceberg through Glue Catalog on StarRocks, we still needed to cover certain important business use cases similar to like the web analytics, right? That requires are relatively fresh or even sometimes real-time or near real-time data to perform the analysis, like building funnels, for instance. The two main cases that we needed to address was the Kafka to StarRocks ingestion and basically different varieties of S3 to StarRocks ingestion. So we looked at the tools at our disposal, and StarRocks provides ways to ingest data, like apart from the simple insert, of course, right? So it provides tools like the stream load, routine load, or broker load, and I'm going to talk about all of them a little bit later. So Kafka to StarRocks is our biggest and sort of in a way most important use case. As mentioned, a lot of our data goes through Kafka, and we do need it fast, and we need a lot of it, and we would like costs to be sort of a measurable. We would like to be able to not measurable, controllable rather. We would like to be able to scale if we need to handle load and to handle spikes, since for e-commerce that does kind of sports merchandise sales, we are having those spikes that are not only Black Friday and Cyber Monday that are sort of a predictable, but like any sport events finals, Stanley Cup, right, NBA finals. So those are all hot market events for us, and we need this additional capacity in our ingestion processes that are going to be able to hold that influx of events. So diving deeper into what we did, so the first prototypes of Kafka to StarRocks ingestions were done using Streamload that uses the REST API to push the data inside. It was super easy to create a prototype that's going to pull data from Kafka, do the kind of very light transformation, since we do, in a lot of cases, we do use JSON that is in message pack, so it cannot be just simply pushed to StarRocks. Certain transformations needed, as I mentioned. And the goal was to try to support 100,000 messages per second and keep up with this within a reasonable cost. So at this point, we saw that we should focus on the pretty large batches sent to StarRocks to get sort of effective and pragmatic with the stream load. But even with the highest kind of batch sizes that we did, we still faced pretty high resource usage on StarRocks side. So we were overwhelming front ends with the REST API calls, and along with that, we were overwhelming backends with the basically tablet versioning, modification, and following compactions and so we realized that this approach is just simply does not scale for us and does not serve the above mentioned purpose. So we moved farther, and we picked the routine load, which is a type of ingestion where backends are running Kafka clients, Kafka consumers that are pulling data from a specific topic. The complexity that we were facing here was the fact that there were certain data transformations, and luckily we were able to reuse some of the libraries that we wrote for Iceberg, Kafka to Iceberg transformations. So with sort of a declarative configuration that is externalized, it was much easier for us to build pretty small Kafka Streams application that pulls the data from our original topics, transforms it the way we want to, and puts it in sort of a stream load ingestible topics. The limitation in this case, or rather the diagram, the flow diagram that is present in this case, is that routine load is built in a way that only one topic could be used per table. So if our source of events contains multiple event types, but we would like them in the different tables, that effectively means that our application should publish data into multiple topics. So we were able to handle the required 100K messages per second. We were also noticed that we can drastically improve performance of the ingestion, reducing the compute used with using it says batching on the screen, but it's more like we were combining events into the JSON array within the messages that we put into this routine load topics. So what that means is that our application, since it's Kafka streams, it could be polling for a certain window or time or message count. Then we're combining those messages in a single JSON array and then putting a single messages with a multiple table records within that array. And this kind of proven to be super effective with regards to compute and IO on our side. Another point is when we were communicating with StarRocks, we were told that like around 300 routine loads were tested on a single cluster, and cluster was doing fine computationally. At this point, we're running around 800 on a single cluster, and we do not see any issues with that. We achieved low CPU and memory footprint. We were able to have certain elasticity with regards to a big like influx of Kafka events in here. Those are handled pretty good, but as usual, there are details that you have to watch into. One of them is basically your routine load config, right? Your parallelism, how many threads you're using. Do you really need that many threads, right? Can you trade off this for the data freshness, let's say? Then basically the polling intervals, the error tolerance, right? This is a super important part. So whether you would like your ingestion to happen, or in case there are issues with data quality, you want it to immediately stop and alert on that. By the way, there are no routine load related alerts off the shelf provided by StarRocks, and that was one of the things that we had to kind of write down ourselves. So we have certain jobs that are actually pulling this data from StarRocks and putting it along with the off-the-shelf metrics that StarRocks provides for Prometheus, for instance. The other kind of interesting thing is that this is an event ingestion, right? So we are pulling events, and we are kind of constantly appending those events. They are not like overriding some previous data or something like that. But that doesn't mean that you are limited to append only functionality, right? So within actually both stream load and routine load, you can have change data capture functionality. So whatever comes in could be considered insert, update, or delete, and you have the capabilities to treat it that way. So this is like a super important feature as well. We are starting to adopt it for a lot of our use cases. The POC has been great so far. Let's move on. So this is how the flow looks like on our side. As I mentioned, like the input topic, multiple output topics per table, as it's written on the diagram, right? And then what we use is that our transformation or flattening library, in this case, what it does is it works out of the external configs, as I mentioned prior. But what it also does, it gets the destination, the table schema from the StarRocks. So it always knows what to expect on the destination size, despite maybe some inconsistencies in a config. And we do embrace the sort of auto mapping feature, which means that it's a no-op for us to handle new fields. So whatever comes into the event, if new fields are added to the event and there are matching fields on the storage size and the transformation is possible between the two, we are it is a no-op for us. So we can ingest those new fields right away. So let's move on to S3 to StarRocks. So how the data could be loaded from S3. What we found extremely useful in this case are use of external tables. Those are limited to certain like specific subset of formats that are supported for such tables. But the simplicity of use is drastic. So if you have, say, a hype style folder on S3 that contains Parquet files or ORC files, you can easily create an external table on top of it and use it as either directly in your queries or as in our case, just copy it into a StarRocks native table. We found this super useful for a bunch of use cases, especially those that are not Kafka related, right? So we have sources of data that are not based off Kafka, that they could be based out of the Redshift, Oracle, MS SQL, and for these, like using S3 as a sort of a middle ground, proven to be pretty important. Along with that, right, for the formats that might not be supported as an external table, the broker load, that's the third one that I want to talk about today, also proven to be very useful. So what broker load does is that you can again point to the your S3 files, let's say containing CSV data, and then establishing certain rules, you can ingest this data into native tables on your side. This is also extremely kind of powerful, flexible, and useful. We started with just bringing that functionality directly to our orchestration layer. So we had orchestration jobs that used configurations and were able to pull the data from source, right, from the source on S3, and put it into the destination within the native table at StarRocks. That way, actually bringing all the needed data to for building analytics going forward. But let's accelerate a little bit. So let's go to the querying and data modeling a bit. So the table types. What we found extremely useful are primary key and duplicate key tables. And they actually serve a very different purposes. So the primary tables are a little bit costly with regards to compute during the insert, because we are regenerating or updating an index that exists for primary keys. But at the same time, they're much faster on selects, on querying, and they allow updates for existing records. At the same time, duplicate keys for the, say, append-only data, extremely useful as something that you can use to speed up the search, but at the same time don't care that much about data uniqueness at this point. It comes at a price though, which is inability to update the data. So you would need to reload the data for, say, certain partition if you would like to say, like, forcefully deduplicate it. So those are both a very useful tools. You have to kind of go to the documentation and go over it to be sure that you're using tools wisely, like for instance, like a string usage in primary keys, right? So can you make it shorter? Can you not use the string? Can you replace string? For instance, if it has like a numerated amount of value, can you replace it with integer and so on? All those kind of usual tricks in the data engineering. So going forward for the data model, right? So the challenges we faced with the data modeling is that our data is essentially a JSON and our schema is evolving. What we found from kind of practical and practice and experiments, or rather prototypes and experiments, is that the JSON didn't actually work for us for tight query requirements. So the JSON extractions are computationally heavy and might not be that effective for your cases. On the opposite side, right? Trade-offs, always trade-offs. JSON is extremely useful with regards to schema evolution, right? So you don't have to take care of your JSON fields. Whatever comes there could contain like a new fields, altered fields, and some other data. But from the practice perspective, especially with the like arrays-like structure hidden within the JSON objects, the querying and extractions are proven to be costly and slow. So what we saw is that a flattening, so to say, and using like the flat tables where your data is mostly simplified to avoid using arrays or complex structures could be a better pick for some of the fast query use cases. Along with that, what we saw is that with the introduction of the struct type supports on StarRocks, we saw that a lot of cases could be very comfortably handled with using struct data types for tables, even though we saw certain penalty with regards to performance on the structs containing arrays, for instance. But the structs that are just like a merely a collection of objects, like a map-like structure of objects, we've been seeing a pretty good result for that. The digging deeper into structs could be costly, but it usually pays for itself having data structured. The downside of structs is probably the fact that you have to have a pretty kind of concise and effective schema evolution that's going to capture your schema changes and immediately reflect them within your data. Probably last point that I would like to highlight with regards to the flat tables is that by flattening certain kind of arrays and making arrays, transforming arrays into a separate table, bringing this amount of kind of joins on the way might kind of slower your queries drastically. So that is like a kind of usual trade-off in data modeling. Another point that I would like to highlight here is how important this is to make sure that your partitioning is effective and your tablet size is within certain boundaries. So what we saw is that the recommendation with regards to having a tablet around 1 GB of size worked very good for us in most of the use cases that we faced, meaning that apart from like usual suspects like skewed partitions and things like that, making sure that your partition and bucketing makes your tablet not too small and not too big can guarantee you a good writing and reading speed on top of StarRocks. Um, Going forward, so the AMV or asynchronous materialized views plus query rewrites, it is a magically powerful tool. With power comes responsibility, and you need to be very careful with regards how you build your AMVs. It has a lot of configurable moving parts in it, starting from making sure that you're not refreshing too often because your source and destination partitions are mapped in effectively, saying that you have kind of much larger partitions within your AMV, and then any small tiny change in your source table triggers updates on a big chunks of your AMV. So this is in a way an anti-pattern. You will always have a background kind of compute use on the cluster if you have something like that. Along with this, the way the updates of the AMV updates are transitioned into the specific tasks running on the back end also should be watched carefully. So what is the maximum amount of concurrently updating partitions? So what is the amount of the partitions that you use to look back and refresh actually? Maybe there is some data that is you're not refreshing, so you can save a little bit on that. So again, to the rescue. This is like analyze and explain. So use all the tooling that StarRocks provides, explain queries, analyze UI for the query analytics that you can enable. Watch for usual suspects yet again, right? So pushing down predicates, partition pruning, make sure this happens. Obviously 100% check the query performance improvement section on the StarRocks documentation. Make sure you're utilizing things like collocation for super fast joins, because you can actually enforce collocation, which is a very useful feature. So you can assign a collocation group on the table, and not only it's going to make sure that all your tables are partitioned and bucketed in the same way upon creation, so it's not going to let you create a broken collocation. So also from performance standpoint, it was super useful for us. Last bit about query performance is shuffling. So watch out for the data shuffles. So what we've noticed is that in certain cases we can exceed the maximum 2 GB size for the like RPC transmitted chunks in between the backends, and our queries were getting kind of very slow because of that. So we had to redesign certain queries, and in some cases even go as far back as data modeling to prevent that from happening. So also check all the variety of sort of tools and tweaks that you can get from the engine, right? So also what we notice is that certain use cases or certain queries could be drastically improved by using things like multi-stage distributed aggregation control. So again, please go to the documentation. This is something that can provide you at least the starting point for you lookup. So what do we have now? What is our current state? As I said, we are using struct tables along with schema-based Kafka events. For that, we had to design, implement, and strictly control schema evolution. So whenever the source event is changing, so basically whatever goes into Kafka being changed, we are trying to immediately update StarRocks side just to be able to map those two. Bhanu mentioned that prior, but I just want to reiterate here that we do support the DBT library, sort of a curated data sets that could be obtained from the data sets that we have on the sort of a lower layers. So useful tools for those into DBT. Apache Superset, we're running it on top of StarRocks, and it provides us all-in-one analytics experience. So you can go there, your data sets is there, you can combine, you can slice and dice your diagrams, your dashboards, and in the end, this is a finished product. So we do use a tooling called KubeDev. They have like both open source and paid offerings as a semantic layer, where it proven useful to offload like the cubes creation and similar functionality from some of the BI tooling and have this on the platform side managed by us. It worked better because of like reusability in this case. Of course, we created an addition to like a text to SQL capabilities of our platform, where again, as Bhanu mentioned, you can ask human language questions about the data, and you're going to be provided with runnable SQL scripts that you can transform into superset dashboards, for instance. All those changes had a huge business impact on all the sort of places of BI, analytics, market, storage, warehousing, and so on. So we are very proud of what we did, and sort of the business and the company leaders are pretty satisfied with the outcome. Wrapping up here, some numbers, right? So we have multiple thousands of tables, views, AMVs on a single cluster that we manage, multiple petabytes of Iceberg data. Druid is no longer used. We replace it completely with the StarRocks, and it is a kind of big area of savings for us. Snowflake usage reduced cost. Snowflake's usage itself, like the footprint, reduced by 25%, and that provided us with like around 90% cost savings, just replacing some of the use cases, for instance, for Tableau with the StarRocks. And then what is happening right now, and it was mentioned by the Bhanu yet again, but I want to reiterate, right? So we are a one-stop shop, and we would like dashboards to be built within minutes using our stack. And this is a huge progress compared to hours, days, or even weeks as it was before. So what is next for us in here, right? What do we think we're gonna do? Next? Of course, more AI. So a lot of capabilities on improving what we have at this point, along with introducing new functionality like multi-data set capabilities of the like conversational chatbots, along with like a new data sets creation, something like of Snowflake's Cortex AI, right? So as I mentioned, we pushed or replaced Snowflake use cases with a lot of with a lot of StarRocks things. And now what we want to do, we want to have like the cherry on top of it, just to pull a bunch of Streamlit widgets and diagram building capabilities onto our platform, since the Streamlit IO is actually an open source product. So you don't have to, it's not required for you to use Snowflake to get all advantages of the tool. Of course, more automation, right? So we're having more and more moving parts in the system, and schema evolution and like a DBT library publishing is not the only kind of thing that we do. Our North Star, our end goal, is the sort of a touchless onboarding of the new databases and tables. So at this point, it exists in a semi-automatic way. So there's a human interaction needed to actually approve changes that are brought in. What we think is that this probably should be done completely automatically. We are looking forward into enhancing the disaster recovery, backup, and restore capabilities with cluster metadata backup and restore, something that is coming or possibly already landed. Sita can correct me here, on StarRocks, because we do value our metadata. We would like it to. We would like to be able to restore our clusters in case of disaster as soon as possible. And along with that, last but not least, so the ultimate goal is the unification of all the BA tools underneath the StarRock platform. So we still use a variety of these, namely Tableau, Power BI, MicroStrategy, and we're moving towards either replacing those drastically, leaving certain footprint, of course, because they have some functionality that we won't be able to restore. But we would like the StarRocks to be a kind of go-to platform for the data that's going to be fitting in. And on that, I'm done with my slides and ready for Q&A. Thank you.
Thank you, guys. Thank you so much for doing this. Thank you so much, Oleksiy and Bhanu. Now, there are a few questions already submitted by the audience, so we're gonna go through them now. Also, if you do have a question, now is the perfect time to ask. Okay, so actually, first I have a question. So, what was the biggest challenge adopting Iceberg into Fanatics, right? And how did you overcome those challenges?
I can take this one from practical standpoint. I think Bhanu can talk about the organizational struggles in here.
Yeah, go ahead, Oleksiy.
Uh, so basically, there are kind of two pieces of the problem here. So one is how to make sure that the onboarding or migration is seamless to the teams, right? So the tools are useful. You can help them, but at the same time, you don't have to kind of babysit each and every sort of a data set that's going through migration. You need to make sure that like there's a feature completeness compared to any solutions that they used before. Along with that, like any new thing is scary. So a bunch of work on making sure how to explain the details on what is Iceberg, why exactly this move is performed, and what are the benefits for sort of each and every team within that. What else? The organizational parts, right? So basically delivering the message, making sure all the sort of like orgs within the company, all the teams are having needed knowledge and resources to consider migration, and they do understand the benefits that are coming with it. So mostly, I would say mostly this, of course, like a bunch of technical challenges related to running Iceberg on EMR and like a Spark integrations and early versions and issues with open source software that we found. So
Yeah,
those
just to
are
add to that, purely from a adoption standpoint, is easy. It is important to provide tool sets for migration that will dramatically reduce teams' ability to move into any new platform here, Apache Iceberg. So very early in the game, we introduced a tech stack called IceMaker, which basically creates Iceberg tables from any kind of source, be it Kafka, be it S3, or be it like Iceberg to Iceberg. So that was a very strategic decision that was introduced, and we built that tech stack. And the second part is obviously introducing Iceberg into the pipelines itself. Spark is very heavily used at Fanatics for data processing. So because of the DBT core and that infrastructure that we have provided, it made teams to actually create the newer data sets using DBT core, but the older existing pipelines is a minimal code change required to use Iceberg and then write to Iceberg.
Thank you so much. Actually, looking at the Q&A, we have 10 questions left. Yeah, let's go through them quickly. If we don't have time, I think we can get to all of them, right? Let's try. If we don't, well, we're gonna reach out afterward with the answers. So first, for OLAP, do you use MDX interface or just SQL interface?
Um,
SQL?
Just SQL. Okay. The second question, that's for us, for the CelerData team. I would need to check on GitHub. Well, is routine loader extensible? Think about able to integrate other messaging system like SNS, PubSub, and etc. Uh, Not really extensible. So if you want to support anything other than Kafka and PubSub, we actually have to implement them. So if there's one that you use as you like and you would want a routine load to support, please file a GitHub issue, please. Thank you. The next one is Fanatics using a shared nothing StarRocks cluster or a shared data configuration. It is not clear since there's a mix of external catalog, glue, but also the use of broker load.
yeah, I'll take that question. Actually, a very great question, very interesting one as well. We started with shared nothing, but we want to really adopt shared data clusters going forward. But yeah, that's where we are.
Okay. Just to add to that, right? So there is like shared data and shared nothing, right? That's like StarRocks concept, right? That's like storing your data in StarRocks own like optimized format, right? In our own file format and our table format. And for Iceberg, that's like external data lake, right? That's open table format, managed like Parquet files, right? So you can use like a shared nothing cluster to directly query um uh, Iceberg table, or you can use a shared data cluster to directly create Iceberg table. The main difference would be like the materialized views you create, right? Is that the materialized view share data or share nothing, right? Okay, next one. Can DBT using StarRocks update on Iceberg tables with this architecture, or you use internal table for gold layer? Do you use Okay, so DBT on Iceberg tables or DBT on StarRocks internal table for gold layer?
Yeah, we predominantly use DBT core for iceberg to iceberg transformation. That is kind of
Mm-hmm.
paid path. But we do have the capability to use DBT to create native tables on StarRocks from StarRocks native tables. Though the use cases are like pretty low at this point in time. But from a
Mm-hmm.
capability standpoint, you could do both.
Thank you. How big is the StarRocks cluster? How do you compare StarRocks to Trino?
That depends on your data volume and use case. So here, as we all have said during the presentation, we are using Iceberg as like the primary store for the data. So it is on S3. You're not physically moving the data into StarRocks cluster. So you could actually keep your StarRocks footprint pretty low, but still support very vast data on the lake. That's where the beauty of the platform comes in. But now you would still have certain use cases where it makes sense to store data natively because you want to support very fast queries, supporting real-time dashboards. That is the point where you basically pivot, and then you might want to store the data natively into StarRocks. But you want to keep it like low to keep your um, cluster sizes and the costs associated with that from an instance standpoint low, so that we can support both the use cases.
Yeah, great. And also add to that, if you want to like accelerate, like some of the hard partitions, right? You can actually create a materialized view, that
Yeah.
only contain like the latest partitions, right? Just like a one-to-one, like the same schema, right? So that way you take advantage of StarRocks, our crazy low cardinality optimizations, our co-location, right? Indexes, and all of the better statistics, all of those benefits, and you can just cache, like
I
cache
would I
part
would
of the
even say
partitions in the MB.
I would even say you can enable data cache first, even
Oh
before
yeah,
the
that's true.
AMVs, right?
Yeah,
So basically, you might not even need the AMV, just enable the data cache.
yeah.
And in case your partitions are hot, right, you're kind of pulling the data pretty often, you have a fair chance of that data being local to the StarRocks already. So you're not going to be reaching out all the way to Iceberg to get it. So there are options here. Thank you.
Yeah, that is true. I mean, there are like many levels of craziness you want your performance to be, right? So like the lowest, right, is native Iceberg without cache, right? And you want it to be a little faster, turn on cache, right? And then you can turn that, into a materialized view. So optimized format, another copy you don't have to manage yourself, but it's another optimized copy, right? If you want it to be run even faster, you can do transformations on that materialized view, right? So basically like 4 layers of performance, depend on your use case, right? Okay, so next, can you help me understand what is getting your way from adopting OBI tools to StarRocks and CelerData?
This is very organizational and predominantly because if folks are used to certain platform for so long, then it's very tough to steer that ship from using that platform to the new one. So that's the challenge. I think it is not unique to Fanatics. It is a challenge across different things. But here the way to actually approach this problem is to show the capabilities and show what is it that you can do with a new platform that you can't do otherwise with the older platform. I think approaching the problem that way would be the most important one. For example, adopting StarRocks with low catalog and then having a simple user interface like StarRocks, you could actually see all of your data. You could discover your data in one central location. Whereas if you're using some legacy tool, like for example, MicroStrategy, you will have to have a ton of engineering effort to basically go and surface those data sets to play around. So naturally, it is enticing for the users to adopt the new platform because the capabilities are a lot more and adoption is easier.
That makes sense.
Yeah,
Next question.
just a final one on
Continue.
this one. No technical, no technical issues, no technical blockers to do that. So they are not technical.
Thank you. Appreciate that. Next question. In what environment does Fanatics operate StarRocks? VM like EC2 or Kubernetes environment like EKS? And why?
EC2.
EC2.
So
Okay.
the short,
We
yeah.
use go ahead, Oleksiy.
So the short answer is EC2. So we've heard about running StarRocks in a container environment. It just suits us more in a lot of ways, since we are very cost cautious, so to say. So it is much more comfortable and in a way easier for us to do the horizontal scaling of our cluster in case of like high impact events, and then at the same time possibly scale the storage, so we can just add EBS volumes to EC2 instances and remove them whenever the peak is past us. So yep, that's the longer answer. Thank you.
Yep. Thank you. The next question. Did you need to apply additional configuration to create Iceberg faster, or was you just using like native configuration that's efficient enough?
No special configuration from what I can recall, right? Sita has a talk about what was done in StarRocks to make it super fast working with Iceberg. So please take a look. Everything should be there. We're not using anything special with regards to StarRocks to Iceberg. What we do is just we apply the best practices to the queries that we write. So some of our tables are pretty big, right? Like petabytes and petabytes of data. So it is super important to make sure like you are querying within a certain partition, right? And so on. So I would say for us, this is more important rather than some specific configuration. And like with an asterisk, we have enabled data cache. So this is probably the only thing I can think of. Thank you.
Yeah, just to add to that, obviously following Iceberg best practices are extremely important. How you partition the data, how you sort the data, and how do you compact the data. That's so critical for any platform to give better query performance. So that goes without a saying.
Yeah, Yeah, Iceberg is basically like a data warehouse on Parquet files, right? So your old like data warehousing tricks and best practice, and still apply, right? Sorting and indexing and partitioning and prune all of the data you can, right? And also like keep your Iceberg table maintained. Those go a really long way.
Yeah, and also to add to that, we have observed that if your table structures are normalized and they're flat instead of going through nested data structures like JSON structs,
Hmm.
the
Yeah,
query performance is better. The joins work
yeah,
a lot more efficiently. So it is something that you would want to consider when you're adopting this.
yeah. Keep everything columnar, right?
Keep
And that
everything
runs so much
columnar.
faster.
Yes.
Yeah.
Yeah.
Okay, the next question: were there cases where you had to create JSON data? Um, if so, what performance target did you aim for on average, and how many seconds does it typically take for JSON?
Can you repeat the questions? I didn't get.
So, do you guys use JSON, and how much like a performance hit do you get like while querying JSON when compared to something that's like pure columnar?
It varies drastically. It varies
Yeah.
drastically. It depends on your JSON. So I mentioned it briefly during the talk before. So having a nested structure that are in turn could be having like multiple arrays in them. So
Mhm.
basically your JSON field contains a set of fields. One of those fields is array that contains another sort of a complex structure that contains arrays as well of other complex structures. So it really depends on how nested your data is and whether there are arrays in there. From our practical experience, we found it inefficient for ad hoc queries to do JSON extraction. Those are heavy. Those are consuming a lot of compute. So for the specific cases that are mentioned here that the use of JSON is unavoidable, what we prefer to do if the query is not meeting our performance goals, we are just hiding transformations under AMV.
Yeah. Thank you. Thank you. Appreciate that. Next question. Only two left. What primary benefit of CelerData over StarRocks self-managed do you feel are the most important?
I can take that question. Um, we had amazing support from CelerData, right? Like in the sense this is a fairly new product, and then comes with a phenomenal promise. But sometimes you will have to have that nicer support to make sure that things are running smooth and things are optimal. And the documentation of StarRocks improved pretty dramatically over the last several months. But like you always want to have that kind of a helping hand, so that way you're making sure you're taking the right calls. That's what I would put it as.
Thank you. Next
Yeah,
question.
so from the
Yeah, go ahead.
practical perspective, this is like
Yeah.
a version changes and certain scaling procedures. So this is more like a lower level.
Okay, so if you are you interested in CelerData, check out cloud.celedata.com and sign up your 30-day free trial today. Last question. How much of a performance hit of a shared data configuration versus a shared nothing cluster for queries?
I think we touched on that already. So I think like from our perspective, our use cases are different and they are different by nature, right? So we know when we need data near real time, we need it fast and we need like avoid any sort of on the fly transformations and stuff. So those are actually native tables for us. So we purposely made that choice. With regards to like direct comparison, our cases on top of Iceberg are usually do not require us to for the fast responses. But I think we mentioned this multiple times before. it's relatively easy to test for a specific use case and get like the apple to apple comparison, right? So
Yeah.
put the data in Iceberg, put the data in the native table, and compare how it works. Enable cache for, enable data cache, right, for your Iceberg tables. Enable query cache for your native tables. Compare the two. Then you can try building AMV on top of Iceberg, as Sita mentioned, and just compare the two and see how it works. What is the compute use? What is the query latency? Read versus write speed, and so on. So those are all kind of those small details, and yeah, I think anyone can answer like it's like 30% slower or something of that sort. It
Yeah.
really very much depends on the case, but everything is in your hands. You can get the answers for your specific use case yourself. Thank you.
Yeah.
Yeah, just
Thank
to
you.
add to that, some of the metrics that we have are we collect about a terabyte of data a day, and then when we store the data into StarRocks native versus we query that from Iceberg table. On the native, we see usual like your P95 to be about less in milliseconds, in hundreds of milliseconds is the query response time. But on the Iceberg, it'll be between 5 seconds to 10 seconds. It's still fast enough, but that's the comparison there. But again, it depends on your data modeling, and then it depends on your size of the data and how it is partitioned on Iceberg. So those things are extremely important. I'm talking to our case.
Thank you. Yeah, it really depends on your use case. I mean, for every single, it's different, right? Your query profile, how your data distributed, right? If it's on Iceberg, like you said, like smaller files, or is it well maintained, right? Is it big
Yeah.
enough, like Parquet files, for us to read, right? Everything's different. So every scenario is different. So definitely, check it out yourself and do a lot of testing. That's all the question we have. Thank you so much, and sorry for going over time. Thank you so much, Oleksiy and Banu. Thank you
Thank
so
you.
much for joining us today, and thank you, the audience. Thank you so much for joining us. And we'll see you guys again next time. Thank you. Appreciate that.
Thank you.
Thanks,
Bye bye.
everybody.
Thank you. Bye. Thanks.